Welcome to this explainer. Today we're going to unpack the incredible hardware, the physics, and the sheer financial mechanics behind Israel's Iron Dome defense system. Whether you're an engineering nerd, a student of modern economics, or you're just trying to make sense of the technology that's constantly in the international news, we're stripping away the rhetoric today. We are going to look purely at how the system actually operates from the ground up. So let's dive right in.
Here's a quick look at our roadmap. We'll start with the aerial threat itself and the anatomy of a battery. Then we'll zoom into the engineering of the Tamir interceptor, walk through a split-second interception sequence, and finally wrap up with the overarching economics of defense.
All right, Section 1, the aerial threat. To really understand the Iron Dome, we've got to look at exactly what it was built to face, which is short-range rockets and mortars that leave virtually no time to react. Originally created by Rafael Advanced Defense Systems and Israel Aerospace Industries, the deployment timeline here is just fascinating. It officially went operational in 2011, and right away, just a year later, during a 2012 conflict, it knocked down 421 incoming rockets. By the time the 2014 Gaza war rolled around, that number jumped to 700 interceptions. So this wasn't just built in a quiet lab, it was tested, tweaked, and refined in real time, right under the pressure of active hostilities. Now, the crucial point here is this highly publicized number, 90%. Since its launch, military spokespersons claim the system has maintained a 90% success rate, successfully intercepting thousands of threads bound for civilian areas. That is a massive statistic, and it's one that has totally reshaped how the region handles aerial threats. But, it makes you wonder, how does it actually pull that off? That brings us to Section 2, Anatomy of a Battery. The thing you have to realize is that the Iron Dome doesn't operate as a single, giant, monolithic shield. It's actually broken down into individual, self-contained batteries. And every one of these batteries relies on a continuous, high-speed loop of data between three specific pieces of hardware. First up, you have the radar unit. This is scanning the skies and can track up to 1,100 different targets within a 100-kilometer radius. Second, there's the Battle Management Center, which is basically the brain processing all that radar data. And third is the firing unit, which usually consists of 3 to 4 stationary launchers, each packed with 20 interceptor missiles. To put this into perspective, Israel is currently protected by 10 of these active batteries, and they are entirely mobile, meaning they can be packed up and moved as threats shift around. A single setup provides a protective umbrella covering roughly 150 square kilometers. That's nearly 60 square miles, which turns out to be just about the perfect size to shield a medium-sized city or a cluster of highly strategic installations. But here is the system's real tactical genius. It's not just about firing missiles. It's about knowing exactly when not to fire. The Battle Management Center calculates the exact trajectory and the predicted impact point of an incoming rocket in real time. If the math says that rocket is going to land harmlessly in an empty field or the ocean, the system literally just ignores it. It lets it fall. And as we'll see a bit later, this filtering process is absolutely crucial for the system to even exist economically. Okay, moving to Section 3. Inside the Tamir interceptor, let's peel back the outer shell. Manufactured by Raytheon, the interceptor missile itself is called the Tamir, and honestly, its physical dimensions might surprise you. When we talk about advanced anti-air defense, we tend to picture these massive, towering munitions, but the Tamir is actually incredibly compact. At just over 9 feet long and weighing 198 pounds, it's barely larger or heavier than a tall person. Yet, despite being relatively small, it packs a highly effective range of up to 43 miles. If we break down this compact interceptor from nose to tail, we find several highly specialized sections all working together to guarantee a hit. Up at the very front, the radome protects sensitive electro-optical sensors that are constantly talking to the steering fins. Right behind that sits the fragmentation warhead and a specialized fuse. And then at the back, a solid propellant motor provides the massive thrust needed to get it out of the launcher, while the rear nozzle and fins allow for crazy, dynamic, last-second maneuverability in the air. Now, the absolute key to how this whole thing works is the proximity fuse. The Tamir doesn't actually try to hit the incoming rocket directly. It's not trying to be a bullet hitting another bullet. Instead, it uses a laser-controlled mechanism to sense the exact millisecond it is within 10 meters of the incoming threat. The moment it crosses that 10-meter threshold, it explodes in a specialized fragmentation burst, knocking the threat right out of the sky with a massive cloud of shrapnel. And it does all of this mind-bogglingly fast. Fired by that solid fuel motor, the Tamir screams toward its target at Mach 2. That's twice the speed of sound. This sheer velocity is absolutely mandatory, because a short-range rocket might only be in the air for 15 to 30 seconds total. You literally just have seconds to react. Which perfectly sets up Section 4, the interception sequence. So, the alarm sounds. What actually happens next? Well, it kicks off a literal race against time and physics, requiring completely seamless communication between all the components we just talked about. And there is zero margin for error here. Here is the rapid-fire sequence. Step 1, the radar detects and tracks the threat. Step 2, that tracking data instantly flows to the Battle Management Center, which runs the math to predict the impact zone. If a populated area is in the crosshairs, boom. Step 3, the launcher fires a Tamir missile. And finally, Step 4, the missile's internal sensors take over, guiding it to within that 10-meter window before detonating. The wildest part? The system makes these life-or-death calculations autonomously in the blink of an eye. But, as always, real-world physics matter immensely. Depending on where the battery is located compared to the incoming rocket, the angle of attack completely changes the game. A head-on collision, that's the ideal scenario for maximum fragmentation damage. A 60-degree angle also works incredibly well. However, if the interceptor approaches at a 90-degree perpendicular angle, you get a much higher failure rate simply because the explosive fragmentation tends to scatter away from the incoming rocket rather than right into it. Finally, let's look at Section 5, the economics of defense. Right behind the advanced radar and the Mach 2 intercepts is a really stark financial reality. This perfectly illustrates the extreme economic asymmetry of this conflict. Think about this. Locally manufactured Qassam rockets cost about $80. Grad rockets might run about $1,000, but a single Tamir interceptor, that costs around $50,000. You are essentially launching a $50,000 piece of highly advanced technology to destroy an $80 piece of crude metal. Remember that tactical advantage feature we talked about earlier, the one that ignores rockets headed for empty fields? This economic imbalance is exactly why that software is vital. If they fired at every single $80 rocket, the defense budget would be completely bankrupted in a matter of days. And when you scale up those interceptor costs and then factor in the radar and the battle management systems, the price tag for just one single Iron Dome battery reaches an estimated $150 million. To maintain 10 active batteries and constantly restock those $50,000 missiles takes an incredible amount of capital, which is why the system relies heavily on hundreds of millions of dollars in financial backing and supply from the United States. This leaves us with a pretty heavy realization. As military analysts point out, while the sheer monetary cost is immense, the alternative for the civilian population living under that umbrella is simply unthinkable. We call this the Iron Dome paradox. The system carries an astronomical financial burden, yet the preservation of civilian life renders the cost effectively priceless. So I'll leave you with this final thought to consider. In the landscape of modern asymmetric warfare, is a purely defensive engineering marvel truly sustainable when the economic scales are so heavily tipped against it? Or does the ultimate value of human life make the price tag entirely irrelevant?